Hi all, good morning, good afternoon, good evening, depending on where you are in the world. Welcome to the first of our 2022 webinar series. We will be doing a series of webinars from April 2022 up until June 2022, and hopefully we'll be doing more throughout the year as well. So the first webinar will be looking at the analysis of used oil and counterfeit fish oil using the Pearl liquid transmission FTIR accessory. My name is Edmund Lo. I will be your speaker today. I'm one of the product managers at SpecAc in Orpington, Greater London, and I look after FTIR accessories for SpecAc. So if you have any questions for me, feel free to contact me directly via email, phone, or even Microsoft Teams, and we can look at some of the products and applications in more detail. So in terms of oil analyses, the challenges with oil and lubricant analysis is that machine oils degrade over time by picking up contaminants before undergoing chemical change. And this degradation needs to be monitored to achieve a balance between performance and lifetime of machinery. But as the oil degrades, very often it becomes more viscous and harder to sample effectively. And so the purpose of today's presentation is to talk about how the Pearl might be more advantageous compared to other FTIR accessories and FTIR techniques. So in this slide, we talk about which SpecAc product is best for you. At SpecAc, we specialize in a wide range of FTIR accessories, as you might already know, with our single bounce ATR in the Quest or the Golden Gate being very popular products within research and industry across the globe. So the single bounce ATR is considered one of the simplest measurement techniques, but the effective path length is very small, as you can see on the left-hand side in the diagram there, with the very small evanescent wave. And this small effective path length then leads to a very small absorbance intensity in your FTIR spectra. And so it can be very difficult to detect oxidation products and soot using single bounce ATR. So in terms of increasing your sensitivity, it might be better to use a transmission technique. And in terms of the accessories, we have the liquid transmission Pearl or the Omnicell. So the Omnicell, again, is very popular amongst universities, especially around the globe, and of course within industry as well. And it's very good for flowing a clean sample through it, especially for non-viscous samples. But if you happen to have a viscous sample, the Omnicell will require disassembly in order to spot your viscous sample on the window. And this could lead to reproducibility issues. And this reproducibility of the path lengths is particularly important when building an accurate calibration plot involving progressively more aged oils. And so we believe that the Pearl solves all of the issues above. The Pearl utilizes a transmission technique and it's very easy to use, just as easy as ATR technique. And it does so by using precision engineered oyster cells that reset the repeatability to the same path length. And so the Pearl solves the issue of not having enough sensitivity, so it increases your intensity of the spectra, and it also allows you to analyze your viscous sample without dilution. The star of today is, of course, the Pearl liquid transmission accessory. We have a set of oyster cells that offer fixed repeatable path length cells from 25 to 1000 microns. We offer two different window options in the calcium fluoride and zinc selenide, and you can control the angle of the oyster cells by having wedged or parallel oyster cells to control the fringing pattern depending on your end application. And so the Pearl is a very simple and easy to use accessory for fast operation and high throughput testing. We offer repeatable path length within less than 1 micron. And as mentioned before, it's especially suitable for highly viscous samples. So some application examples include FAME testing, as we'll touch upon in a few slides' time, essential oils, insulation oil, lubricants, pastes, organic solvents, paints, and UV inks. In the next few slides, we'll be diving into some real-world applications. But just a little warning for you all, the slides will become very oily. The first application we'll be looking at greases and lubricants. Greases and lubricants are important to help moving parts of machinery operate smoothly. Over time, the oil or grease or lubricant, they'll degrade and pick up contaminants, and there'll be a chemical change in the spectra. So we need reliable ways to keep things running smoothly. So as mentioned before, when comparing the Pearl and the Quest single bounce ATR, for example, because the Pearl uses a liquid transmission technique, very often the absorbance intensity will be a lot bigger than the spectra collected by Quest single bounce ATR. And so the Pearl will be more ideal for monitoring trace components due to this high sensitivity. And the Quest would be more suitable for measuring bulk properties. And you can see the difference by looking at the two spectra here. So we'll start off by talking about figure 1 on the left-hand side. In the red spectrum, you've got a spectrum of Castrol grease collected using liquid transmission Pearl. And in the blue spectrum, you've got the Quest, which utilizes single bounce ATR. And in certain regions across the spectral range, you really do see the difference in terms of the appearance of the spectra. So the red spectrum, for example, towards the left-hand side, at around 3400 wave numbers, you see the hydroxyl related broad band. You also see the overtone, and towards the lower wave number in the fingerprint region, at around 1000 wave number and below, you also see some peaks associated with additives and contaminants. And due to the high sensitivity of the Pearl, you see these trace components stand out compared to the blue spectrum, where a lot of these signals aren't showing up at all compared to the Pearl. And if you look at figure 2, which is a set of spectra collected by analyzing DuPont Krytox, again in red you have a spectrum collected by the Pearl using liquid transmission, and the blue is the Quest. And you see again that towards the left-hand side of the spectra at 2000 and 1800 wave number respectively, you have soot and also potentially some degradation as well, which is showing up a lot more in the red spectrum compared to the blue spectrum. So moving on to the next application, so we have fresh versus used motor oils. So service oils like Castrol Magnatec engine oil are designed to minimize wear and tear in engines. Over time, the oil picks up elemental metals, soot, and other contaminants which are visibly appearing in the oil. The Pearl is often used to determine which contaminants are present and the type of chemical degradation that has occurred. Here on the left-hand side, on figure 1, it's just to show you the difference in absorbance intensity when using different path lengths of the oyster cells. So naturally, due to Beer's law, when you use a lower path length, like 25 microns for example, you get less absorbance intensity. As you move towards a higher path length of 50 microns and 100 microns, there is a linear increase in the absorbance intensities. And then On the right hand side, in figure 2, we use the 25 micron oyster cells to look at the degradation of the motor oil. So in the blue spectrum, we have a spectrum of fresh oil. In the red spectrum, we have used oil. And you can see the mode of degradation in this set of spectra, where at around 1700 wave number, you see oxidation and nitration of the oil due to its usage over time. And you can also see a decrease in the concentration of oil over time, and also sulfation as well at around 1200 wave number. And the PEL can also be used to compare oil samples from different manufacturers and different specifications. So here is a comparison of 3 different oils at 25 microns, as you can see in this set of spectra. And so the PEL is a great liquid transmission technique for identifying different molecular signatures before distinguishing between oils from different manufacturers and specifications. In this application, we look at the FAME quantification in accordance to EN 14078 standard. So FAME stands for fatty acid methyl esters. And in this standard, we're looking at quantifying the carbonyl group using 3 different oyster cell path lengths. As some of you might already be aware, there is a climate emergency where governments are looking at green alternatives, including biodiesel. But actually, you can't use pure biodiesel because you would risk damaging your car engine. So you need to dilute it to different percentages of biofuel before using the biodiesel. And so this standard looks at the carbonyl peak at 3 different path lengths as mentioned before. And as you can see in the calibration plot on the bottom, in the middle of the screen, the oyster cell can highly accurately quantify the carbonyl peak at the 3 different path lengths at 50, 100 and 500 microns. And you can see that it's highly accurate because of the R-squared values in all 3 of them. So you're always getting 0.99, 0.99 and 0.99, all 3 of the plots. So this fully demonstrates that the PEL is compliant with this standard EN 14078. And not only is the PEL compatible with the standard mentioned before, but also compatible with these other ASTM standards used across industry. So now we're going to talk about transformers, but not the animation kind. We're going to talk about high voltage power transformers. So mineral oils are very often employed as the thermal and electrical fluid insulator in many power transformers. Thermal and electrical stress over the lifetime of the transformer can cause degradation of the oil through oxidation. And the breakdown of the oil can be monitored using PEL transmission FTIR and principal component analysis, or PCA. So here in figure 1, we have 2 sets of spectra. We have figure 1A and figure 1B. In 1A, it's just a set of spectra looking at the mineral oil in different environments over time at ambient temperature. So you've got mineral oil by itself, or mineral oil in combination with the solid insulator, the craft paper, or more realistically, you've got mineral oil plus craft paper plus the copper. So the copper is just the conductor used as a transformer coil, insulated by the solid insulator, the craft paper, before it's immersed in the liquid insulator and the mineral oil. And in figure 1b, you have a set of spectra measured over time at 120 degrees Celsius. So the oil changes chemically over time at 120 degrees Celsius, as you can see, due to the oxidation of the mineral oil to aldehyde, and hence you see the CH peak at just after 2500 wave number, and also the carbonyl peak as well, due to the aldehyde and carboxylic acid. And then you can use PCA analysis, as mentioned before. So this is a statistical technique to tell you the age of your oil and also which environment it's been in. As mentioned before, the environment is, of course, how the oil has been stored. So it can be just the oil by itself, or in combination with the craft paper and also the copper conductor. And by using this PCA data, we can easily determine the age and the environment of the oil. So that's it in terms of analysing the breakdown of mineral oil under thermal stress. In the next application, we'll move away from machinery and we can talk about more human related sort of application in terms of food and beverage. So a customer in the USA recently used a Pearl liquid transmission accessory to detect fraudulent fish oil. In this application, the customer used the Pearl to analyze fish oil on the market to ensure that the nutritional value is what it says on the tin. And we do that by differentiating between the different ester peaks between oil expressed from fresh fish versus oil from fraudulent fish oil tablets. The reason why we're interested in this application is because fraudulent fish oil in the market could potentially endanger the health of pregnant women. So in this particular example, we have a spectra of fraudulent fish oil versus oil expressed from fresh fish. In black is a spectrum from the fraudulent oil tablet, where we're quantifying the ethyl ester at 1036 wave number. But in the red spectrum from the fresh fish, you don't see the ester peak. And essentially, the ester goes through hydrolysis to create ethanol as a byproduct, which is then potentially hazardous to pregnant women. We strongly recommend using the Pearl accessory for analysing viscous samples. As you can see here on this table, it uses a transmission technique which gives you intense peak intensities, and so you can pick up trace components very easily. And it does so by using oyster cells with very large range of path length options from 25 microns to 1000 microns. In terms of path length reproducibility, They're all very high, but the pearl in particular, we say is better than 1 micron. And in terms of ease of sample loading and cleaning, it's very easy with the pearl and the Quest. Both the Omnicell, it can be particularly fiddly, especially when analysing viscous liquids. The pearl has 2 optical material options in calcium fluoride and zinc selenide, but at the moment it doesn't have a heatable option.
To install the pearl into your spectrometer, tighten the screw to the base plate. Then open the drawer and install a bottom window. The bottom window controls the path length, wedged or parallel, and the material. You can then spot your sample onto the window and then install the top window to complete the cell. Then close the drawer and your sample is ready for measurement. When your measurement is done, open the drawer and then take the top window out. You can then wipe away your sample with a tissue and then wipe clean with some lens tissue soaked in a suitable cleaning solvent. After a few seconds to air dry, your cell is then ready for the next sample.
If you're very keen on determining the path length accuracy, you can download the software from the link as seen on this slide, collect your spectra, and then use the pearl calibration software to then accurately determine the path length. So once you've downloaded the software, you'll be able to find some videos to give you sort of a step-by-step guide as to how to measure the path length accurately for both the parallel windows and also the wedged windows as well. We have a large collection of application notes. Just contact myself or any of our colleagues at SpecAc for a copy of the application notes of interest. And we've recently redone and relaunched our website as well. So any links that you've saved previously from SpecAc, they will no longer be valid, but you can use these links here from now on to sort of check up on any products or FTIR theory material. And also, I believe it's a lot easier now to locate different marketing literatures and application notes as well using our new website. So please do spend the time to check out our new website. It was a wonderful website. We've spent a lot of time on it, and it's been well worth it. It's very nicely done by our marketing team again. So that's it from me. Thank you all again for listening. I hope you enjoyed the presentation. And like I said, if there's anything unclear and you'd like to organise a one-to-one meeting with myself, then you're more than welcome to do so. I look forward to speaking to you again. And if you have any questions, please feel free to type them in the chat box.